Hello, everybody. My name is Mike Garceau. We're here to present a case study and some information about 3M's approach and roadmap related to immersion cooling in the open compute community. I have some individuals that we've partnered with that I'd like to introduce. Phil Tuma, application engineer for 3M. John Gross from Page. You guys are in order. This is great. Mechanical engineer with Page. Carwing Lau, CEO of Allied Control, which is a mechanical integrator doing immersion cooling tanks. And Structure Tone, a general contractor, Charles Benge, director of Mission Critical. And I'm Mike Garceau. I'm with 3M Business Development. So we've got a few topics we want to cover. So a couple will go quickly, and the other one we want to spend a little more time on. One quick introduction to immersion cooling. There's been a lot of talk about that, so we'll probably go pretty quick. We want to give our roadmap for how we want to engage with the open compute community. And then we have a specific case study that we wanted to present to you guys for your feedback and your interest that we think is quite relevant to the community and to this use case. So first, 3M is a manufacturer of fluorochemical fluids that have unique properties. They're non-flammable, have strong safety profiles, have a wide range of boiling points that make them optimal for these applications. And we've been doing it for over 60 years. As you heard, there was a lot of comments and discussions about different working fluids. As always, if you have questions about our working fluids, come to us and we'll give you all the details and all the facts about the properties of our fluids. But we've been doing these sorts of applications of direct cooling of electronics for decades and have a lot of experience with it. And we'll talk about some of that as we go. So I mentioned this, we spoke a little bit outside as well, that our intention is to leverage the OCP community and this working group in particular to help form an ecosystem for immersion cooling. And you saw some of the people that presented already, I think, have a role in that to get IT hardware, mechanical systems, facility designs, and power delivery components that are optimized and take advantage of the properties of immersion. And our first contribution to that today is two things. We're going to show you a concept for an immersion-cooled power supply, and then we're going to present this hyperscale case study. So I will hand it off to Phil. We'll talk a little bit about the concept for an immersion-cooled power supply.
Can you hear me okay? Great. You might have heard, if you were in the presentation earlier today by Alibaba, they mentioned some of the supply chain constraints that have been challenging in immersion cooling. This is an example of one that we've encountered. Conventional power supplies are designed to be cooled by air, obviously, and those power supplies are generally made to operate with fans. So the first thing we have to do, of course, is modify the firmware so that those power supplies will function without fans. But it goes way beyond that. Most of the power supplies we encounter are at least 80% air. A lot of the remaining volume is metal that needs to be, or could be dispensed with in an immersion environment. We have to put a lot of costly fluid into that volume to fill it, and so we'd like to see the power supplies densified. This particular model that I'm holding in my hand is an example, a 10 kilowatt AC to DC power supply. It could fill, takes a mere fraction of the volume of a conventional air-cooled power supply. Those air-cooled power supplies often contain, in fact, they always contain a myriad of contaminants that we have to contend with in immersion cooling environments. Plasticizers in the dialkyl phthalate, PVC, and solder fluxes, conformal coatings, silicones. These all become fluid contaminants for us, and they're unnecessary in an immersion environment. Particularly in two-phase, we don't need heat sinks on these FETs and voltage regulators, most of which could be driven to much, much higher amperages if they were immersion cooled. So one of the things we hope to get out of interactions with the OCP community is to get perhaps power supplies and other components that are more ideally suited to the immersion environment. Moving on now to the actual case study. Just as an introduction, I think some of you may have been confused earlier. There were some presentations that spoke about immersion. They didn't necessarily differentiate between the types of immersion. People do what we call single-phase immersion with oils and other fluids that do not change state from a liquid to vapor. They're pumped as a single phase. The technology we're talking about in this presentation is two-phase immersion or evaporative immersion. The hardware is put in a tank of a dielectric coolant that boils on the heat-generating components, condenses, and then passively falls back into the tank. So everything that occurs within the immersion environment is passive. And heat is shuttled outside the facility to a dry cooler using conventional water and dry coolers. The tank you see on the left there is an example of a 250 kilowatt tank from a cryptocurrency deployment. That particular one houses tens of thousands of ASICs and is one of 160 such tanks in a large immersion cool facility. And I just wanted to make the point for those who may not be familiar with the technology. These tanks are serviceable. They can be opened during operation, and hardware can be removed and swapped just as it would be in a conventional rack. And it tends to come out of the tank completely dry, similar to the way it would in a vapor degreaser. So hot swapping is a perfectly legitimate procedure for two-phase immersion. And with that, I'll pass it off to John Gross. Page.
So one of the main things that we were trying to do with this this research project that we've been working on, this case study, is to take what's already been done right now in the cryptocurrency environment and figure out how we can apply that to a more conventional data center where we have redundancy considerations and many other considerations that cryptocurrency typically doesn't worry about. So we had to determine a baseline for this case because we're comparing a conventional air-cooled solution to an immersion-cooled solution. And so we looked at what is typical for a hyperscale right now, and we had to make a number of assumptions. And so there's obviously going to be some differences between this and what the hyperscale providers do based on who they are. But anyway, we selected a 30 megawatt IT load as our baseline hyperscale deployment for equally sized data halls so that we can look at modularity and phase deployment. We had to pick a location because part of the premise of this study is not only can it be done, yes, it can be done, you can pretty much put anything into a box, but how much does it cost to build? How much does it cost to operate? How big is it? All these things come into play. So with a lot of the hyperscale work that's being done in the Midwest, we chose Des Moines, Iowa. That gave us utility rates for our energy modeling. It gave us labor rates for construction costs and so on. We tried to level around a 10 kW server cabinet as our air-cooled equivalent and a 150 kilowatt tank. As Phil mentioned, the cryptocurrency users are currently seeing 250 kilowatts, in some cases potentially even higher, using ASICs boards with the 150 kW tank that allows us to stick with GPU-based hardware, which is more readily available. We also tried to do something that cryptocurrency typically doesn't, which is designed towards a tier 3 standard. We wanted to have redundancy in there because we know that the vast majority of users are going to have redundancy requirements in here. So we tried to go through and do a comparison between these two solutions, looking at all kinds of physical metrics in terms of how big of a site do you need. That comes into play if you're in an area where real estate is particularly expensive. Construction costs, which we'll get into a little bit later with Charles. And included with that construction cost is how do you go and build and design an MEP infrastructure to support this solution at the tank level. There have been a lot of conversations today about immersion cooling, both single phase and two phase, and a lot of them have been focused on what's happening at the tank. Not so many have actually taken a step back and looked at what the rest of the facility looks like in order to support that. So we did that in this particular case. We also looked at construction schedule. Speed to market is a big thing for a lot of end users. It's huge for the cryptocurrency folks, which is one of the reasons why they chose this particular solution. And then we go through a number of other items here. You can read the bullet points on the slide here.
Okay, thank you. Yeah, as you can see, that's our concept design on the tank, and the dimensions are listed on there. I won't go into that one. But you can see that all the connections to the tank, like power, process water, and telecom, come from above. And this allows us basically to get away without any raised floor. Of course, that's why we have a much more simplified construction process with that. And as mentioned before, for this particular study, we have agreed on 150 kilowatts per tank. And this is being delivered with a proprietary busbar system, very much similar to the OCP busbar system, however modified to go into the tank with a much higher voltage AC. We have rectifiers inside the tank, which are then transforming it to DC. The illustration also shows that the tanks are being aligned in such a way so that you still have ample white space around. Despite of that, we can achieve a very high power density of about 34 kilowatts per square meter. And as mentioned before by John and by Phil, this is not just a concept design. We are displaying here a study, of course, but we have used this in the cryptocurrency world already since 2012. One of our installations in the Eastern European country of Georgia, not the US state, is 40 megawatts, and that's a facility which is running since 2015, non-stop until today, so just about 2.5 years. And aside from that, we are setting up already another facility in another Eastern European country of this will have a maximum IT load capacity of 120 megawatts. We have already completed the first 30 megawatt phase. As we speak, we are starting with the next 30 megawatts phase, and by the end of the year, we will have completed 120 megawatt of immersion-cooled data center. So that's not just a concept design anymore, but really a commercial installation.
Back to Jenna.
Okay, so how do we go and take these tanks and implement them into a facility? So for this comparison, as we discussed before, we have an air-cooled hyperscale, 10 kW per rack. In an attempt to not try to get too aggressive with the system infrastructure, something that a lot of end users would look at and say, well, I wouldn't even do that in my data center today. We avoided the direct evap and some of those other cooling systems here. Instead, we went with water-cooled chiller plants with water-side economizers, hot aisle, cold aisle containment with chimney-style racks, perimeter crays, an architecture that should look fairly familiar to everybody here. We maintained N+1 throughout. We have concurrently maintainable distribution, both on the power side and the mechanical side as we go through. And as you can see here, we ended up with a facility of approximately 13 acres, including all the circulation, the build rooms, all the admin support space, so on and so forth. We took all of those same ancillary spaces, the support spaces and whatnot, and we carried those over one for one, no optimization, no changes into the immersion cooled solution. But then we went and we said, well, how small can we make the data center itself when we go from 7.5 megawatts per data hall of air-cooled racks to 150 kilowatt immersion cooled tanks? We ended up with a substantial reduction in the square footage of the white space itself. And a substantial densification. We also got rid of crack galleries. We got rid of the chiller plants. The chiller plants themselves were actually replaced with pump rooms, and we'll get into the schematics of what that looks like later. But at a high level, you can see we took a 13-acre need and we shrunk it down to a 7-acre deployment. One of the big things here with the building configuration is because we have no open loop water systems, we have no cooling towers, et cetera, we don't have any large sources of water to worry about. We do have a cooling loop, a process cooling loop that is a closed loop system. The heat rejection equipment for the immersion cooled solution is completely dry coolers. No evaporative pre-cooling media is required. So one of the things that does allow is if an owner wanted to even further consolidate the space requirement, you can put the coolers up on the roof. You don't have the leak concerns that you have with a water-cooled plant. So we get into the electrical topology. There's a lot of comparison here that you can read through. The two big takeaways I want to point out to folks here is one, the reduction that we have in the electrical demand because of the mechanical system change, getting rid of all the compressorized equipment. We went from a mechanical load estimated of 11 MVA for the 30 megawatt down to 3 MVA. So not only is that a tremendous savings in CapEx, there's a lot less space required for that electrical infrastructure and distribution. The other thing that I wanted to point out is if you look in the middle of the chart here, we talk about the UPS. Under the air-cooled scenario, we've got 2,500 kVA of UPS modules. And then in the immersion-cooled, we have 2,800 kVA. So that sounds kind of backwards. We're talking about reducing loads all the way through, but now we're increasing our UPS. The reason we actually show that is that because of the extreme densities that we're dealing with here, your mechanical systems need to be on UPS backup power. The IT equipment stays cooled so long as the liquid level in the tank is at or above the top of the circuit boards. If you have a power failure and you don't have water continuously moving through the cooling coils in your tanks, condensing that liquid back in, then your liquid level starts to drop. So this whole system was designed based on the need to put that mechanical infrastructure on UPS power and carry it through. The mechanical topology, those of you who have designed, built, operated, lived in the baseline case, you know about all the compressor maintenance that has to be done on the chillers, all the water treatment that has to be done with the condenser loops. There's a lot of equipment in there, a lot to deal with. So in the immersion cooled situation, we've gotten rid of all the compressors. We've gotten rid of all of the Cray units. We've gotten rid of all those fans associated with it. The tanks themselves have control valves which modulate to maintain the liquid level and the temperatures within the tanks. So that's how you're handling all of your heat within the space. From the plant side, we've gotten it down to where all you have are circulating pumps and dry coolers. It's the only thing you have left to reject the heat from the tanks out to the outside world. Because of the operating temperatures of the fluid itself and the IT equipment, we don't need any evaporative pre-cooling of any of the heat rejection media. This is a 100% dry system. And so you see when we get down here to the estimated annual water consumption, we're talking about going from nearly 300 million gallons a year for a 30 megawatt load down to 0. And obviously the PUE delta here. One thing I did want to point out here briefly about the PUE delta, between these two and the PUE numbers we show, we actually ran a full-blown energy model on both cases here. The energy model took into account UPS losses, transformation losses. We did a lighting design. We factored in all of the key components that actually go into calculating a PUE. So I have seen in some cases before where people are reporting PUE numbers that sound almost too good to be true, and you dig into it and you find out, well, there's key bits of information missing from that. This is a complete PUE calculation with all the factors accounted for. So on the telecom side, this is another area that isn't frequently taken into account, and that is we're putting so much more compute into a single location that we have a much lower number of terminations that need to be made. We're going from gigabit LAN to 10 gigabit from the servers to the switch, and then from 10 up to 100 from the switch to the core here. But just the sheer reduction in the number of servers, greater than a 4-to-1 reduction in the server count, that reduces our quantity of switches. That requires or has a corresponding reduction in the number of terminations that have to be made. So there's a tremendous savings on the telecom cost also associated with this.
All right, something different than heard today is we actually have cost for this, where we're actually deploying a data center. We have gone to a savings of 4.8 million per megawatt is what we're looking at here overall, which in your standard air-cooled system, that number varies depending on your architecture of what you put in. We picked a standard here that we could work off of, which is 11.6 million per megawatt, and we've got that down to 6.8 million per megawatt. Competitive numbers, we stuck it in middle America. Where you choose to build, we should still be in the same ratio of savings. Where we found the most savings in this was, of course, one of them is scale. But where we really found savings was in the amount of qualified, competent labor required to build this. Something we didn't talk about on the electrical infrastructure is the only two pieces of equipment here that are not off the shelf are your generators and your UPSs. The rest of this is pipe and wire, switchboards, breakers, controls that can be bought right off the shelf, right out of a catalog. Lead times are no longer an issue. Right, we go build a data center, we always worry about how fast can we get the equipment here. Moves us into schedule. Moving to schedule, we have a 30% reduction in schedule time, which means a 30% faster speed to market to build this immersion cooled system. Sounds like a lot, sounds like it's too good to be true. We go from a 21-month build, which is really a fast build on a standard data center, to a 16-month build. The savings of that is in the actual fit out of the data hall. We don't have raised floor, I don't have ceiling, we don't have a lot of demising walls, I don't have a lot of complicated equipment to move in and out. We build a box, we bring in the tanks, we hook up piping to them, we get the coolers operating, we move in electrical systems, and there's a gigantic savings in commissioning cost. I don't have it. I have switchgear to commission, I have tanks to commission, they can be factory tested. So speed to market was one of the big items we found, and a lot of it has to do with scale. There's a large savings in the electrical systems because of the reduction in massive amounts of skilled labor I need. I use standard commercial electricians to deploy this system. So that pretty much wraps it up. I think we're going to go on to questions. If anybody has any questions or comments about what we presented here, we had to condense what usually takes about an hour and a half to present. So we've hit the high spots of this.
Thank you. You hold on to that. You're answering the questions, not me.
You were asking if you could get access to the Revit models for the data center?
We'll talk about it.
Yeah.
Yes. Go ahead. Yes, we can make that happen.
I wanted to ask, what kind of power density does this solution become cost effective? You're at 10 kW per square foot, that's pretty high.
Yeah, and that's actually a great question. So the initial purpose of this study was to do just kind of a snapshot in time comparison. We have some data that indicates that when you start getting up to around 65, 75 kW per tank, that's when the solution really starts to take hold as a strong leader. That's also going to depend on the scale at which you build it. We're still working on kind of the next phase of this research study process to identify where some of those breakpoints are, how low we can go on the density before it starts to make sense, how small you can go on the scale before it really starts to make sense.
Can I add something?
Yes.
Yeah, I'd like to add another very important point. We briefly mentioned it before in the presentation, that real estate costs might be also a very important factor. So with immersion cooling, we are able to increase the density tremendously, like having, for example, instead of 10 kilowatts per rack, 20 kilowatts per rack, we have 150 kilowatts per rack. So if you take a look at not, for example, setting up a data center in somewhere in the Midwest, but for example, let's say in metropolitan cities closer to the New York area, right, San Francisco, or for example, if you go overseas, for example, Singapore, Tokyo, Hong Kong, the real estate costs over there are very, very high. So with immersion cooling, you are not only going to be able to save some money on the construction cost itself, but also on the real estate cost, part.
Yes.
Really great job, guys. I think we've seen like immersion cooling, liquid cooling for quite some time in the industry. And like, where do you see like a product adoption life cycle curve, like where this is? Because obviously like there's really good numbers of efficiency and TCO, but like why hasn't the industry fully adopted it? What are the restrictions and limitations in doing so?
Well, I think several of us will have items to kick in there, but you know, from what I've seen personally, it's that the fully developed ecosystem isn't quite there yet. A lot of it is waiting on the IT hardware to catch up. One of the things that makes any immersion solution more cost effective is when you need less fluid. And what allows you to get away with less fluid is the volume density of the actual hardware within that tank. If you were to take a conventional air-cooled server right now, strip the sheet metal off of it, strip the heat sinks off of it, and put it into a tank, you could do that, but you'd have about 90% air. And Phil can probably talk a little bit more about that because he's done those specific comparisons. But that's what I've seen. Carl Wing, I'm sure, got some additional insight.
We pretty much answered it already.
Yeah, I think you covered it pretty well. To characterize, I think we were looking for a characterization of the adoption curve. Much of the adoption is in where the hardware is already highly densified. So supercomputing and cryptocurrencies were the first people to embrace the technology because the hardware was already densified or was easy to densify. So where we're seeing a push into mainstream computing is where HPC OEMs are creating hardware configurations that are designed for immersion. People are seeking out high-density GPU applications, or when you see some of the presentations even today where you can see a roadmap from a hyperscale end user that can influence the entire value chain and change the geometry of the hardware, the density of the hardware. So I think we're at the, I would call it a tipping point to go from adoption in those applications I mentioned in towards very high volume mass adoption.
So we've identified that that is absolutely an opportunity. That is one of the things that we have discussed internally within the team about something to look at for the next phase of the project. One of the things that we do struggle with a little bit is the quality of the heat is not that great for doing things like on-site power generation through, say, like an organic Rankine cycle generator, for example. We're still too cold for something like that at this particular point in time. But there are other places where we can potentially use that heat. We just haven't delved quite into those yet.
What kind of output temperature are you talking about?
This particular design, which was a lower temperature design, was about 127 degrees Fahrenheit. I'm sorry? Celsius, please. Oh, 52 Celsius. So, thanks, Phil. It's in the ballpark. Yes, but one of the opportunities that is there is that there are multiple fluid options out there that have different boiling points that still are compatible with the IT equipment. One of the quick kind of back of napkin test fits that we did here that Phil and I looked at was if there is a fluid that is available today that's compatible with the IT operating temperatures that would actually be able to stay 100% dry cooled in Phoenix, Arizona at Tier 3 and Tier 4 design temperatures, and the answer was yes. Yes, sir.
So this is augmenting the earlier question about the roadmap. Are you able to do anything on a proactive basis with customers to further adoption of this technology? I know, typically going back and value propping as this can enable a different design, hardware densification and whatnot. Have you been able to employ that as a strategy for furthering this, or do you have other strategies similar to that to further accelerate the adoption curve here?
Maybe I could just characterize it as success breeds success. So the most compelling thing that an end user is going to see is another end user adopting. So we do some of our own activities to try to tell the story and paint the vision, but largely it's real-world examples of deployments that have the biggest impact, what I've found. Yeah.
So,
Would you say that any momentum is building towards that? I mean, we've been talking about this for a while, obviously. You did say the hardware has yet to catch up, but do you see any real momentum building other than case-by-case basis?
Yes, I do. There are probably things I can't characterize publicly, but no doubt about it. Yeah, I think the architectures are changing in a way that's going to make this extremely compelling for more and more use cases. So, yes.
One of the other things that I wanted to throw out there, so I'm a consulting engineer, and so I work with different clients every day. This technology actually opens up opportunities that more conventional HPC solutions, for example, might not. I've got one particular client that is completely maxed out on their site utility power infrastructure. They can't. They're completely maxed out, and the utility company has a huge cost to bring additional power to the site because of how far they have to bring it underground, what they have to take it by, so on and so forth. Well, their current HPC operation is around a 1.6, 1.7 PUE, and we showed them the information on this, and they saw the opportunity for something around a 1.07, 1.05, 1.1, kind of depend, in that area. And they said, well, wait a second, if we can go and in our next HPC refresh, instead of putting in the same type of HPC compute we've been doing before, we put something in here. Now all of a sudden, their total power consumption for the site goes down while they still keep the same compute, and that opens up opportunity for them to actually add more compute in there. one of the things that's, and I'm sorry, I'll get to you in just a second. Somebody brought up something in one of the previous 2 or 3 presentations that was a question about the server fans and the power that they consume. So we know that when we take the server fans away, we're actually freeing up critical load off the UPS output. Depending on what manufacturer you talk to, that number has, we've heard range anywhere from 2% up to 20%. So it's a tremendous amount. We haven't even tried in this study to try to level set what the actual compute is that you're getting out of your power. We're just assuming, you know, that it's actually 30 megawatts of compute that you're doing here. So there's even further opportunities there.
Great presentation, great work. If you're fully deploying a tank on day 1, so a hyperscale build, I think the design makes a lot of sense. But if you have a client that may be in more of a pay-as-you-grow mode from an IT deployment perspective, is there a compartmentalization strategy or something with the tank design so that you can limit the volume and the cost of the dielectric? Because obviously that's a major component of the cost.
Carwing, do you want to cover that?
Okay, it's a multi-part question. So for the deployment of the tank, there are various ways how to do that. If you have an already existing data center, it's possible, for example, to hook up our tank to an existing water cooling system. So, for example, the tank itself, it's pretty much agnostic in terms of what kind of water cooling loop you're using. For example, you could hook it up to water chiller. You could hook it up to evaporative cooling tower. But of course, what we strongly recommend is to run it with a dry cooler, as mentioned, right?
I'm talking specifically about the design so that, okay, so let's say you have a tank design for 150 kilowatts, let's say, right? But on day 1, I'm only going to deploy 20 kilowatts of IT load, right? Do you have to fully immerse the entire, do you have to fill the entire tank on day 1, or do you have some type of compartmentalization so that I'm not forced to incur that cost on day 1?
Yeah, okay, I get the question, yeah. So, yes, there are solutions to that, so that you can partially deploy the tank. So, for example, only put in like 20% or 30% of the hardware inside, and the rest could be compartmentalized. Yes, that's possible.
Is your distribution system a closed loop?
Yes, sir.
And are the fluorinated chemicals is that a regulated substance?
No. The fluid is not not regulated for transport or use anywhere in the world. Yeah. Correct. And they're actually used, some of these fluids are used to extinguish fires, so they're used as halon replacements. So the safety profile is obviously there.
So if you use it in that case, then it would be regulated.
Not regulated. Well, I wouldn't say that. NFPA doesn't currently recognize immersion cooling as a fire protection strategy, but potentially it is one. Potentially it is one.
We can get rid of the fire protection systems too.
Well, that's also, there's a byproduct of this that we didn't get to, and you bring that up, is we can use a wet system over these tanks. This proposal we put together was pre-action on the whole thing, because we can get so outside the box here that you get the eye rolls. But you bring up the tanks and the fluids. The electrical equipment in here is rated at 30 AIC, and there's no arc flash for your guys doing maintenance because it's dielectric fluid. So it's a safe system to go in and work with the equipment there. There's no arc flash to it. So.
Yeah, one of the things I kind of skipped over a little bit as I was going through the electrical distribution is for the case we did a modification on the design that Carwing's got deployed, but the tanks are 484 wire direct to the tank, so there's no PDUs. So you don't have the footprint of the PDUs, you don't have the arc flash concerns with the PDUs, you don't have the potential fire hazard of all the transformers, et cetera. Correct.
And if the sprinklers deploy, you don't want your gas in there.
That's correct.
Well, that's some bullet
But
points.
by the way, what he said. Yes, sir.
How often you have to recycle the liquid? 1 year?
Yeah, the fluorochemical fluids that are used here have, I hate to say infinite, but an indefinite service life. We do scrub the fluid in situ to remove contaminants to keep it clean. But that's not because of any degradation of the fluid itself. It's just because of contaminants it picks up from the electronics themselves. So you can expect an indefinite service life, similar to a refrigerant in a, an automotive or residential AC system. You typically don't have to change that out.
Yeah, that worked out. That worked out well.
Great presentation.
We really appreciate it. Thank you very much.